Welcome to Advanced Math, Vectors, Unit 12, Part C, page 1 and 2. As always, you should do this on your own using the printed version or the online version. And come look at the video if you're confused or just need a little extra information. So this part is bringing us back into that scenario that was presented at the very beginning of Chapter 12 on vectors. Ms. Hedren of the Xenops Bird Ranch and her Yorkshire Canary enclosure, we haven't got all the information that we need to actually tackle that problem as stated yet, but we're getting there. There's a few more things we need to cover. So this is just here to remind us that we do have a scenario we're trying to solve, and we are going to get there. Just be patient. The bottom of this page has a quick review of the vector concepts that we have covered so far. Moving on to the next, we're going to start off with a little practice from the previous section just to make sure we have a handle on it. So we'll go through this together. So we're given a vector u, -1, -3, and a vector v, 2, 1, and we want to find vector u minus v using components. So to write that out, I would write vector u in components, subtract from that vector v in components, and then in my brain, I'm going to be subtracting like components. So the first component of u minus v is -1 minus 2, or -3. The second component of u minus v is -3 minus 1, or -4. So there's my u minus v done or computed using component form. Now we're going to try doing the same thing using a graphical technique by sketching our vectors on the grid and using angle sum in the graphical method. So first of all, I want to graph vector u, and I just pick an arbitrary, thinking about what direction u goes, and u goes to the left and down. So I'm going to start I choose a different color. I'm going to start my vector somewhere on the grid here. So there's my starting point. Vector u travels 1 unit to the left and 3 units down. So the endpoint is going to be here. And I'm going to sketch this as a line with an arrowhead going there. The fact that my line isn't perfectly straight doesn't really matter. This is just connecting the starting point to the ending point. It just needs to be clear where I'm starting and where I'm ending. So that is vector u. Now I'm going to add to this a -v vector. So -v is going to be the components of v, but negative. So it'd be -2, -1. So I'm going to add a -v to u. So the -v vector goes 2 units to the left and 1 unit down. So that's its ending point there. If I start it, rather, at the tip of vector u and go in the direction of -v, I'm going to go over here. So there's my -v vector. So what I'm doing now is I'm adding these two vectors together. I've drawn them in a way that does that, or allows me to do that, by drawing them in a head-to-tail format. And now my resulting vector, u minus v, is going to start where the first one started and end where the last one ended. That's my result. That's u minus v. And in component form, I can see that that's 3 units. I'll write it down at the bottom. U minus v is 3 units to the left. That's going to be the -3 is the x component, and it's 1, 2, 3, 4 units down. So its y component is -4. And as you can see, by constructing this sum graphically and getting -3, -4, I'm actually matching what I got when I just went straight from the beginning. I just said, let's just subtract like or corresponding components. So it does give you the same answer. So yes, does your answer with the components match your answer with the arrows? Yeah, it does. Okay. So we've looked at some simple arithmetic with vectors. We've done addition, we've done subtraction, we've done multiplying by scalars, but is there a way or a meaning to the idea of multiplying vectors by each other? And there are actually a couple of different ways that vectors can be multiplied. We're going to focus on one of them, and that technique or that style of multiplication is known as the dot product. And when you write it as the vector u, or one vector, with a dot, just similar to the way you'd use a dot for multiplying any number, and then the second vector. So you're multiplying u times v using the dot product. Anyway, this is how it works. If you've got two vectors, u and v, and if you remembering that vectors don't have to have a particular location, if you join those two vectors together so that their tails were at the same place, you could actually measure the angle between them. Or rather, I should say that there would be an angle between those two vectors if you imagine putting their tails together. So keep that idea in mind, that there's an angle between them. Now, multiplying two vectors together means multiplying their lengths together. So, to start with, if we're talking about u dot product with v, the first thing to think about is we're going to take the length of u, written as the absolute value or magnitude of u, times the length of v, or times the magnitude of v. So it's a length times a length. Now, that's all well and good, multiplying the lengths of two vectors together. But remember, vectors also have this directional information about them. So how can our multiplication capture the direction of them and not just their lengths? And that's where the final component of this multiplication comes in. So fully, the dot product of u and v is the product of their lengths times the cosine of the angle between them. Think for a moment what this means. If the angle between them is 0, that means that the vectors are parallel to each other and pointing in the same direction. If the angle between them is 0, the vectors are parallel to each other and pointing in the same direction. And do you remember what the cosine of 0 degrees is, or 0 radians? Cosine of 0 is 1. So what that means is when the vectors are actually pointing in the same direction, the dot product of those vectors is the same as the product of their lengths. It's just multiplying their lengths together. Likewise, if the angle between the two vectors was 90 degrees, a right angle, then the cosine of that angle, cosine of 90, think about your unit circle, cosine of 90 is 0. So the dot product of u and v, when u and v are perpendicular to each other, is 0. The fact that you're multiplying their magnitudes together is irrelevant, because when the angle is 90 degrees, the cosine of 90 gives you 0, and the whole expression is 0. So the idea here is that the dot product of two vectors is, first of all, multiplying their lengths together. But second of all, you're capturing how much those two vectors are pointing in the same direction. The more in the same direction they are, the more like it is just multiplying their lengths together. In fact, when they're exactly in the same direction, the dot product is multiplying their lengths together. But as those two vectors are pointing in different directions, in the worst case, they're pointing perpendicular to each other, their dot product is going to be 0. So this is a way of capturing the parallelness or similar directionness of two vectors when you're multiplying them together. Coming up next, page 3.